Okay, I guess my sound's off. Great. Okay, so I talked at length last Wednesday about fixed step integrators. And I think the big takeaway of fixed step integrators, right, is that you can make your time steps smaller, right? That's one way to do better. But sometimes it makes sense to just use a better integrator. And we found that a lot of these higher order Runyo-Kuda methods got you a nice improvement in accuracy while still allowing you to get sort of relatively large time steps, whereas time steps sort of limit how many computations you perform. So the obvious generalization of that, right, would be to maybe, instead of sticking to this idea that we're stuck with some time scale and we have to just do as accurately as possible around that time scale, that's the idea behind Runyo-Kuda, would be to vary the size of the time step adaptively based off the problem that we're currently trying to solve. And I guess the motivation for why this would be interesting, and the book really gets into this, is that there's this proof that I sort of glossed over, but we showed briefly in the last class, that talked about how the accumulation of global error is really set by two terms. And one of those terms is the truncation error, right? So that's the physical property of the solver you've chosen. So Runyo-Kuda methods have a lower truncation errors, so the global error grows slowly. But the other property that really affected how quickly global error grows was the Lipschitz constant, which is an upper bound on how quickly the right-hand side of your differential equation changes. And this is important because basically, as we know, differential equations by definition have a bunch of different slopes associated with them at every point in the domain. The right-hand side returns a different vector. And so you could imagine that you could define something like a local Lipschitz constant that tells you the rate of change locally. And so we know the error depends on how quickly the function changes. So why wouldn't we just adapt our time step based off of how quickly the function is changing? And this is the whole idea behind variable step methods, is that if I have a lot of different time scales in my problem, sometimes I can take giant steps because the problem's not doing anything interesting. Other times I might want to take much smaller time steps because it's really rapidly varying. Okay, and there's kind of this is a little bit hand wavy, but there's actually quite a bit of lore here. But you can think of these as sort of a poor man's version of higher order optimization. So in optimization, we saw that Newton's method used curvature information to decide what kind of steps to take. Variable step methods, you can think of having some sort of quasi-Newton-like structure to them because we're adapting the size of the step we take. Okay, so the last class I was using a chaotic system to show off all these different fixed step integrators. So I'm going to use a different chaotic system today just for fun. So I'm going to use a chaotic system called the Hadley model. This is another 3-variable chaotic system. And this is, I think, one of my favorite ordinary differential equations because it has one of the most interesting attractors I think I've seen. So this is just some differential equation, right? It's given a 3-vector, it spits out a 3-vector of time derivatives, and we're going to numerically integrate it. And when you solve that using just a built-in Python solver, the attractor looks something like that. So it's this really sort of crazy fractal object that doesn't have any obvious symmetries associated with it, which I think is pretty interesting. And I can even try plotting. So this is coordinates 1 and 2. It's a 3-variable system, so I could try plotting 2. There we go. And you can see that it has no obvious symmetry if I rotate about the different axes when I plot it. So this is kind of weird fractal thing. It's like a bird's nest or something. And I really, these are just the 3. So this is a 3-variable dynamical system. So it's like an X, Y, Z. So I'm just plotting X and Y, or X and Z. And the one thing I like to point out about this attractor that might motivate why you'd care about variable step methods is you can see that it has this really sort of diffuse region out here where not a lot of trajectories make it over there. So it's very sort of hard to see when I plot it. But then it's got this sort of dense core here. And so maybe there's some intuition that there's variation in the attractor density, that maybe there's going to be a lot of different time scales present in this problem. So we might benefit from being able to adjust the time scale of our integrator. Okay. So that's the Hadley system. This is the super expensive trajectory, but we're going to compare against a much shorter trajectory because some of our integrators aren't quite that fast. So we really are going to try to see if all the integrators we implement today look something like this reference trajectory, just like we did in the previous class. Okay. So the idea with variable step method is pretty straightforward. So if I have a fixed step method, the toy model of a fixed step integrator is always the forward Euler method. So I literally make one call to my gradient function and take a step along that direction, scaled by the time step or learning rate effectively. And we saw that that the error accumulates as effectively a geometric series where every time I take a step here, I have some value that I observe, and then there's some true value that I should have seen. And the rate at which this global error grows depends on some accumulation factor that's basically the gap between what my Euler returned as the gradient and the true value. So basically every time I take a step using Euler's method, I gain a little bit of error. That little bit is the local error, but over time it grows to the global error across many steps. So the obvious way to reduce the error, right, would be in Euler's method to make this delta t as small as possible. And in fact, it could be shown that in the limit of delta t goes to 0, Euler's method becomes exact. That makes sense because that's just the definition of the derivative. Okay. So as a couple of people pointed out last class, right, we could do all this fancy integration stuff to try to do this as accurately as possible, but we could also just try taking a smaller time step and see if we do better. So one way that you might imagine trying to adaptively reduce your integration step would be to just check at every time step whether or not you could have taken a bigger or smaller step, basically to see if your error has converged in some general sense. So the idea here is pretty straightforward, which is that if I fix some delta t, I could try computing my next value of my function just by taking a step directly along delta t, where I evaluate my function at my current position. But I could also instead take two half steps, where first I take a step along half of delta t, so I make a little half step, and then I take another step that gets my other half of my time interval. So effectively, delta t has passed, just whether I allow myself to take one big Euler forward step or two half Euler forward steps. And this is called the two-step Euler method. And you can guess that in the limit of, say, a function that's just increasing linearly, these should always give me the same answer, because whether I take two half steps or one full step doesn't matter if the right-hand side isn't changing. So I can use that idea of taking two short steps and comparing it to one big step to get an estimate of whether my integrator is going to have a truncation error from the fact that I'm taking finite steps. So all I'm going to do is I'm going to take the full Euler step. I'm going to compare that against my true solution. And then I'm going to take two half steps and compare that against my solution I saw when I took the full step. And that change in error, we're going to call something like the relative error accumulated by taking a large time step. So the heuristic that we can back out then for how to choose our time step is at every point that we want to update the position of our particle, we can try taking two half steps, try taking one full step. If the half step method gives us a very, very different answer than taking the full step, then we can guess that our step size is probably too high. And so then we're going to adaptively reduce the time step. And the way you do this is going to vary depending on all sorts of schemes, but I'm going to do this just purely geometrically. So basically, I'm going to take two half steps, see where I end up, take a full step, see where I end up. If those are super different, I'm going to say that my time step is bad, and I'm going to decrease it by this factor of 0.9. And I'm going to keep doing this over and over again until eventually I get a point where my two half steps and full step are the same to within some tolerance. And that's going to be the relative tolerance of this adaptive integration scheme. And the intuition here, right, is that basically this is going to always shrink the time step until I get to a point where effectively my function is linear, because the effective linear regime is where the two half steps and the full step should give me the same answer. So I'm just going to keep shrinking until I find the regime where that's the same. Okay, so that's the Euler two-step method. And it's a very simple way of doing this, but it actually works surprisingly well, even for super chaotic systems. So I'm going to show my implementation of that, and then we'll walk through how it compares to this global and relative error stuff. Okay, so my two-step integrator, I'm just going to implement each of these as its own class just to simplify things. So it's going to take a DT, just like we saw for fixed step integrators. But this DT is really going to be something like a starting guess, because as we see, we're going to be updating this over time. So we're going to call this more like a maximum DT rather than the absolute DT. And then the other new thing I'm going to introduce is a relative tolerance. And this is going to be how big of a difference between my two half steps and my full step I'm willing to accept as being close enough that I can go ahead and update. And you can imagine that the smaller I make the relative tolerance, the more I'm going to have to winnow down delta t over time. And then I'm going to have maximum iterations. This is just going to be however long I allow myself to continuously update delta t before I give up and say that I'm not going to burn more compute on it. So all this is the same as fixed step integrators. I just pick up a relative tolerance, which is a truncation condition on my step size update, as well as another truncation condition that prevents me from updating to infinity. Okay, so my integration ends up being a little bit more involved, but a lot of this stuff is very boilerplate. So just like every other integrator, including built-in, I'm going to take a callable right-hand side. So this is an API where I give it the current time, the current position, it'll spit out the right-hand side. I'm going to give it upper and lower bounds of the integration interval, and then I'm just going to give it my current position, so my 3 vector for this system. Okay, so all this stuff is the same as we saw for fixed step integrators. The only fine point here is that I'm going to record my starting value of dt, and that's because we're going to start updating that in the loop. Okay, so then all the logic of the integrator is in principle very similar to the fixed step integrator, which is I'm going to use a while loop because I'm going to keep updating time until I hit the upper bound of my integration interval. I prefer this to using a for loop because we're using variable steps, so I actually don't know how many steps I'm going to use a priori. So I'm going to use a while loop here instead of a for loop because I don't know the number of steps. Then the actual logic of the 2-step rule is I'm going to try doing a candidate update with the full step. So this is the full Euler step where I just go out by delta t. And then I'm going to do the 2 half steps where I go by half delta t. Then I use that value to take another step with half delta t. So then my error signal is going to just be the difference between where I ended up after 1 big step versus where I end up after 2 tiny steps. And this is going to be the signal I use to decide whether my integration time step was small enough. Okay, so then the real logic of this comes down to this function, where it basically says that if this error is lower than my tolerance, that's good. That means that the 2 half steps and full step agree with each other. So then I go ahead and accept the update. So then I update my time. So I say, okay, I can move forward along my integration time. Then I store my solution that I just recorded, update the time, and then I'm going to reset my dt to whatever my default is for my integrator. So my escape condition is this. That's good. That means that I've converged. Okay, so if this doesn't trigger, though, that's where we take advantage of the fact that we're in a while loop. So if you look at this, this only triggers if this is tiny. So if this isn't tiny, this doesn't activate. So then we skip over this. We skip over this, but then we do trigger this else condition. And then the else condition is where we implement this shrinking of the time step. And you'll notice we shrink at a rate that depends on the scaling factor as well as the error relative to the tolerance that we've defined. So this ends up shrinking our dt. Then we check to make sure that we haven't gone stuck in some like infinite thing for 10 to the 8. Usually that won't happen here, but hypothetically we have a stop condition to prevent that. But then because I haven't actually updated my time, I've just updated dt. T is still at what it just was. This while loop remains triggered. So this while loop will keep running until we eventually accept something, because that's the only way to move forward in time. And the hope is that, every step we do all this stuff, we keep shrinking dt. Eventually we trigger this condition. Then we finally update t, and eventually t reaches the upper bound of the integration integral, and we finally escape. So the while loop here is just a really compact way of doing both the incrementing across time and making sure that you don't take a step until your error has converged to below your relative tolerance. But the actual real meat of this function is just these lines here. Okay, so in this loop, I'm going to continuously update the position of where I am in my domain, but I'm also going to keep updating my dt. And then once I finally accept a step, I'm going to reset it. So my dt can decrease continuously, but once I accept a step, I'm going to reset it back up to the default, which was 1e to the minus 3. Okay, so I can go ahead and try integrating using this. Let me make sure that's in memory. And hopefully this still works like it did yesterday. And one thing to notice, right, is that when I did these integrations using the built-in integrator, they were super fast. But this Euler 2-step is actually kind of slow. And this actually makes sense because in principle, I'm not just doing t calls to the right-hand side. Because I have this while loop where I can continuously shrink down the dt, within each call to this loop, I could do quite a few iterations. So I end up burning quite a bit of time slowly shrinking my time step. But having said that, it actually does pretty well. So I'm going to go ahead and guess that SciPy is probably the most accurate integrator here because I set the tolerances really low. But generally, we get most of the attractor. You'll notice that where it really chokes is in this really diffuse region. And that's not a coincidence because that's where you're going to be most sensitive to having errors in your stepping. But nonetheless, it's pretty good. At least we got the right domain and all that. So I'd say that Euler two-step does surprisingly well in this problem, given that the Euler method is a very sort of naive integration scheme.
How is the diffuse part? Like, what's part of the error? Like, wouldn't the places with like the greatest amount of change like incur the most error, or is it because of the variables that the region is bigger?
Yeah, that's a good question. Yeah, so I think that I understood it as because it's diffuse out here, you're more sensitive to like you come in, then you go into this really flat region, and then like how far you go out in that flat region depends on sort of initial conditions more. But I agree that it's probably something more subtle than that. It's a bit hand wavy. But at least qualitatively, because this region is sort of flatter with regards to the derivative, you can get a lot more like visible variation there. It's sort of like a slow manifold, I guess. Okay, so one of the things I can do is it looks like my two-step Euler is pretty good. So I can try looking and seeing where I had to take tiny steps versus big steps. So here what I'm going to do is I'm going to plot I'm just going to plot one variable just to get a sense of where things are changing quickly. Then we can compare it to the size of the time step at that thing. Okay, so this is the actual solution, right? So this is 2 coordinates, but I'm just plotting one. So you notice that there's a little bit of fluctuations here. It makes sense. And you can see kind of what happens, which is that sorry about this axis. This top one is my two-step Euler method. The method sort of spikes at these turning points. And that kind of makes sense that my step size spikes right off. It's a little bit out of phase because it basically has to adapt more when it's changing more quickly. So there's this nice sort of symmetry that you see between the actual what the solution's doing and the size of the steps here. And you can see that, like, for example, here, my step size spikes back up. That spiking up corresponds to resetting, but then it really quickly decreases due to this internal logic where it's continuously shrinking here. And we sort of rinse and repeat throughout the integration. Okay. So that's nice. And that suggests that, presumably my two-step Euler is being somewhat adaptive to the context of the problem. So just for fun, I tried comparing that to what SciPy did. So SciPy is using a different integration scheme that is presumably a lot more sophisticated. And interestingly enough, my two-step Euler, which some would call very naive, actually basically gets a pretty similar pattern regarding when it takes small versus large steps. And that gets at this idea that really the size of the step has to do with the local properties of your problem, maybe mixed a little bit with the properties of your integration scheme, but there at least seems to be some general agreement between the two regarding when you have to take big versus small steps. It's not quite absolute. Like you can see that SciPy did something fancy here, but you can at least capture this idea that there are fast and slow regions with this attractor, and that's reflecting the size of the steps you take. Okay, so just for fun, I can try taking that time step and plotting it on top of the original attractor, and you can start to see kind of what happens here, which is that the step size is actually pretty big in this region in the middle here. So in other words, this region in the middle is kind of effectively less sensitive to the time step. I was able to get away with much bigger updates, but really it's out here and over here where I actually had to shrink my step size to some really tiny value. So these areas I'd say are sort of more stiff, and so they're harder for the thing to get accurate updates. So I had to use much smaller time steps like 0.01 instead of 0.1 over here. And one thing I'll just point out is that I used an initial step size of 1e to the minus 2. So I have a global ceiling on how high my step can be, because after every update to the step, it resets to 0.1. And then it's going to continuously pull that down. And it looks like it had to pull it down quite a bit by a factor of 10 in order to capture all the variation here. Okay, so that's interesting because actually, I'd argue it tells me something interesting about my system, which is that it sort of has these regions that are less sensitive, and then there's these other regions that are more sensitive to the stepping. Okay, so that's a variable step integrator, and that's like I like two-step Euler because I think it's the simplest example of how you could have an adaptive time step. But it turns out that basic idea of taking a trial step, taking a higher precision trial step, comparing the two and deciding if your step is sufficient, that's basically the whole idea behind an entire family of integration schemes. So Euler's two-step scheme is an example of a general class of schemes called embedded integration methods. They're all based around the idea of taking two steps. Okay, so no one is using Euler two-step for anything serious, but that basic idea is captured in modern embedded methods, which involve taking these two steps. And the one that actually is used a lot is the RKF method. So this is a lot of lore, so we'll go through this sort of systematically. But we talked about how before Euler is an example of like a zeroth or first order Runge-Kutta method, where I basically take one update or two half updates. And the whole idea with Runge-Kutta methods is that you can take that logic really far, so you can perform a bunch of additional intermediate evaluations. So a pretty common integrator that people use for variable step is this really ugly Runge-Kutta method, where you actually perform 6 evaluations before finally taking an update. And the values of these coefficients come from linearizing around the solution, so I'm not going to try to argue that they're particularly interesting. But the idea here is I take my Euler step, I use that intermediate value to find some new value of my position, I feed that to get K2, I then use K2 to get K3, and you'll notice I also have K1 in there, and it has this whole sort of nested structure where each K depends on everything that came above. And then I finally triumphantly take one giant step that's some linear combination of everything that came before. And the argument is that this should be more accurate than if I had just used K1 or some fewer number of terms. Okay, so that's, kind of ugly, but the butcher tableau is, I think, a better way of summarizing that, which is that this is your K1, that's your K2, and then we combine all of those previous values together using this sort of agreed upon sort of combination of them. Okay, so embedded methods look different than standard fixed step methods. And the reason that they look different is because they don't just have one update, they actually have 2 updates. So I don't just take one step based off of all of the previous values they just computed. I also take another step that's a different combination of the previous values. And this is the whole idea with embedded methods, which is that I actually have 2 updates that I define as a function of my previous coefficients. And those 2 updates are going to be what I compare to see if my relative error is lower than my threshold. Okay, so the intuition here is that this bottom row, or the top bottom row, this row here of the butcher tableau is going to combine K1 through K6 using these coefficients and take a step. And you'll notice it uses everything out to K6. So it's going to use this line in order to get a candidate update. So I'm going to argue that this row is going to give me an update that's analogous to my 2 half-step Euler because it used this higher order information, so it should be more accurate. Okay, so then this other row, this other row of the butcher tableau also uses the previous solutions, but it doesn't use the last row. So I'm going to argue that this second update should be less accurate than my first update because it doesn't use all those intermediate evaluations. So this row I'm going to argue is going to be like taking my full step Euler. So embedded methods have 2 output rows, and these are going to be the 2 things that you compare to see if your relative error is lower than your threshold. And I argue that comparing this high accuracy solution to this lower accuracy solution is analogous to comparing the 2 half steps to the full step Euler. That's the basic idea here. Okay, so that's a lot of like coefficients and stuff, but the intuition is just we do 2 Runge-Kutta updates, one of which we expect to be more accurate than the other, but then we compare to see how different they are as a truncation condition on our time step size. Okay, so just like before, we're going to do an update based off of this one, an update based off of that one, and then based off of how different those are, we're going to once again shrink the time step using a geometric series proportional to 0.9. What's up?
So you're doing 2 time steps. One is more time consuming than the other one. How are we saving? Like how is the adaptive rather than just doing a batch thing? How it's like.
Yeah, so why wouldn't we just always use the more accurate one? So the real reason that we do the 2 steps is to see if we don't need to further shrink this step, because it's quite possible that I use both the bad step or the bad update and the good update, and they give me a really different answer. And so then I don't really want to take either one. I want to shrink my time step and recompute both. So I'm using the difference between the more accurate and less accurate to really probe whether my problem is anywhere close to the regime I want it in. But you're right that like I keep shrinking, and then once they agree, then I can take the more accurate one.
So the point of doing these 2 steps method is not for the time efficiency, but more the accuracy also.
Yeah, guarantee that your accuracy is to within the relative tolerance because your 2 solutions have converged. And I sort of like it because I think that, you know, if I didn't know anything about like how to pick an integrator and I was just sort of like using Euler's method, one way that I might naively try to see if I've gotten the right solution is I would get some solution. I would then integrate with a smaller time step. And if I got the same solution, I'd say it looks like I've converged. And this is basically doing that on a per update basis. Yeah. Okay, so RKF, you know, I'm not going to try to read too much into the butcher tableau here, but importantly, we're going to do 2 updates after we computed all these intermediate steps. Okay, so if you really are a big fan of looking up coefficients, this is what this looks like when you implement it. And I'm going to emphasize that the structure of this is almost identical to the 2-step Euler, right? My constructor needs an initial time step. That's going to be the maximum step I ever take. A tolerance condition, that's going to be when I finally accept something. And then this just prevents me from updating my time step infinitely. So then all this is quite literally copy paste from Euler. And then the only thing that's different here is now I have to do all these intermediate K1, K2 evaluations. So these really nasty things where I compute K1, I feed it to get K2, et cetera, et cetera. So I have these 6 numbers, and using those, I can get both my sort of naive update as well as my more refined update that used all 6 of them and should have better properties. So that's the only difference, because once you ignore that, everything is now the exact same as my 2-step Euler method, where I compute the difference between my finer solver and my coarse solver. I see if it's less than my relative tolerance. If it is, I'm happy, and I go ahead and I take the step. After taking the step, I reset back to whatever my default step was. That's 1 e to the minus 3 here. Otherwise, I shrink my time step and I rinse and repeat over and over again. Okay, so the danger of a method like this is that because I have this condition here, it's quite possible that in order to take 1 update, it'll run this 10 to the 8 times. So this can get really, really slow if my problem is super stiff. So the hope is that I have some certain level of smoothness in my problem. If I have really discontinuous problems, this could get super slow. However, if I don't have this break condition, you know, it'll just run that while loop forever. So I do need to have some safety here. Okay, so this is identical to Euler 2-step. I've just added this code here, and really just this code here is what differentiates the 2. Okay, so the hope is that this is going to do a lot better than Euler 2-step. Let's see if that comes out to be the case in practice. So here I'm gonna deliberately pick a really large maximum step here, and I'm gonna hope that my solver can figure out if it needs to use a much smaller step. And once again, we're going to compare this to a SciPy integrator that I trust is more accurate than my implementation. Let's see how fast that is. Okay, actually pretty good. Okay, so this one does a little bit better, but it still doesn't quite capture this lobe structure. So you can see that it still messes up this area over here. We saw before with the Euler 2-step that this was the area where you had to use a really small step. So it makes sense that this is more sensitive over here. But you can see it looks like it got some of this middle structure a little bit better. So when we ran the Euler 2-step, we had a little bit of issues where it got this weird sort of pseudo orbit here where it had higher density here than I think it should have. And here it captures a little bit more of the complexity here where there's not just like an orbiter here that I can focus on. So arguably this got a little bit more accurate. And perhaps more importantly, this also converged way faster. So my Euler 2-step, I was kind of nervous it wasn't going to run in time, but this one ran super fast. And that kind of makes sense because basically you pay a lot more computing all these intermediate values, but then these next versus half updates should be more accurate to compensate. And it turns out that balance between more compute that you're committing to versus not knowing how many times you have to update tolerance balances out in favor of using this higher accuracy method. Okay, so this is a faster method that adapts my integration time, and it looks like it did pretty well. So once again, I can compare the actual true trajectory to what I saw, or to where I took small updates. So when I do a plot like that, I get something like this. Hopefully that's good. Cool. Okay, where this is my true solution, so this is what it's actually doing, and then this is where it took steps of different sizes. And here it looks like my Runya-Kuda method is actually getting pretty close to what SciPy does here. So you'll notice that like SciPy, when it's using this fancy built-in integrator, has these like double peaks here, and it looks like my implementation also got that double peak. So it looks like the integrators, or the fancy integrator and my own implementation, are starting to converge regarding what they think is a good time to take big versus small steps. So that's nice that we're sort of converging to what might be called a state-of-the-art integrator. And I'll mention that the method that SciPy is using, this Redao method, is a much fancier, but it is a variable step integrator, but it's too much code to try to fit in a notebook. Okay, so variable step embedded methods I really, really like because I think that embedded methods capture the intuition behind why you would use variable step methods, while still being conceptually simple enough that you can kind of debug what they're doing. They're just trying to see if your error is below some relative tolerance. Okay, the last thing I'll say about embedded methods is that since I think 2016 or 2018, MATLAB's default integrator has been dormant prints. And I think that that's also the default in Python now. I'm not actually sure what ODE uses now. And dormant prints is an embedded method. So whenever you use like some built-in integrator that you've been given, it almost always defaults to an embedded method because they're very, very conceptually simple. And the really critical thing with embedded solvers is to control your relative tolerance, which basically tells you how far your less accurate and more accurate solver can drift from each other before you accept a step. So relative tolerance is really critical for picking an integrator or for picking the parameters of your integrator. Okay, so variable step methods are pretty awesome and they generally work pretty well. And in my research, we basically only use embedded methods. We don't use implicit solvers that often. And you'll even find that's true for stuff like fluid dynamics, that explicit embedded step is usually easier to use than implicit. Okay, so that's about what I want to say about variable step. So now I'm going to change gears and just talk about a couple of other integration methods that you might see. And these next couple of things are going to be kind of a tour of different things in integration. So we're not going to spend that much time on any given one. But before I finish talking about variable step, are there any questions on that? All right. So the other kind of integrator that you might encounter, and this we won't get into, but you can imagine there's entire courses that talk about this at this institution, would be cases where you have stochastic forcing present in your system. And we basically kind of already did this when we talked about Ornstein-Uhlenbeck processes, because an Ornstein-Uhlenbeck process effectively shadows some continuous time dynamical system. So I'm not going to get too much into this other than to mention that the simplest way you can implement stochastic differential equations is almost the same as the way that we implemented the Ornstein-Uhlenbeck process. And the idea here is that if I have some Euler-like update, I can just add a random vector to my output, and that will simulate having Brownian motion driving my process. And it turns out that when you do this, it has its own name as an integrator. It's called the Euler-Murayama method. But in principle, it's actually just taking an Euler update and adding random noise to it. And that simulates having your particle subject to Brownian forces acting on it as it's traversing through some landscape. Yeah, what's up?
I still can have conceptual issues with like any stochastic differential, like stochastic differential equation in the continuous case, where like what it actually means to solve the continuous stochastic differential equation if like the stochastic component is non-differentiable.
Yeah, I think that there's a lot of right, there's a lot of stuff that's sort of being swept under the rug here, right? There's whole debates as to like the whole Ito versus Stratanovich interpretation and all that. I think that we're making an assumption on smoothness, right? We're assuming that without the forcing term, right, you're not going to have any discontinuous jumps. And then over some reasonable interval of integration, the kicks sort of average out, so you have effectively some like smooth force. So I think that when you take like a finite time step with an update like this, you're sort of assuming you have like an average kick amplitude that's smooth, even though the kicks themselves are discontinuous. But I agree, there's deep lore there. Yeah, and I'll mention one of the physicists I really like is Tim Sauer. He's a dynamicist at George Mason, and he has this whole series of notes about using Ito calculus for, in his case, he's interested in financial time series, as you can imagine. So these notes are pretty good and they're pretty concise. So plug for those. Okay, but the simplest stochastic integrator that you're going to use is just adding a random vector, and this is basically what we did with Ornstein-Uhlenbeck. And so this just looks very simply like an Euler integrator with a noise term added to it. So all this code is just equivalent to a fixed up Euler update rule. Because this isn't variable step anymore because I was too scared, it just takes a fixed step that stays the same, and then I'm going to bake in the noise there. And then the update is just going to be my standard Euler update, and then I just going to add a random Gaussian vector centered at 0 in each component to it. One thing that's kind of interesting about these, and we saw this before for Ornstein-Uhlenbeck, is that the magnitude of the noise term scales with the size of your time step. That kind of makes sense because if you think about it, like if I wait longer before looking at a stochastic process, it could travel further. And it turns out that the mean square displacement grows linearly with time. So you need to scale the step by square root of t. So importantly, I actually have to use dt to scale my noise. So if I take a really big time step, my noise has an effectively higher amplitude. And that's just due to the properties of Brownian motion. But other than that, this is just an Euler update thing with this noise term added. And conveniently enough, just like the traditional Euler method, Euler with stochastic updating does converge to being correct in the limit of delta t goes to 0. Again, that makes sense because we're just using the definition of the derivative there. But the nice thing about this is there are some guarantees on it, which is not always true for stochastic integration. And here I just did it with some small noise and I got my same attractor, but I got noise on top of it. So no surprises there. One thing I'll mention is that, for people who do a lot of stochastic integration, the times that this gets interesting are cases where your noise kicks you into regimes that aren't accessible in the deterministic dynamics. So you can sort of see this here where like I had this really sort of what I call a slow manifold here. But when I have the noise, I get this dynamics over here. And when I compare that to the actual solutions, I pretty rarely end up in this regime. And this is where I think dynamics get interesting, because this is the regime where you get stuff like stochastic resonance and stuff, which is where you access new parts of your phase space because you have noise coupled to your integrator. And if I had something more exotic, like maybe I had like geometric noise, so I actually scaled the update size by this, then this would actually really get crazy where you could access entirely new types of attractors just by having noise present. So even though this is kind of boring, it just looks like, noise added to my deterministic trajectory. This idea of being able to cross a Bayesian because you have this stochastic forcing can give rise to sort of qualitatively new types of dynamics. Yeah, and actually, I'm just going to see if I can get it to do something bad. Okay, I got it to diverge. Great. Yeah. Yeah, okay. You start to see it takes really big excursions well outside the attractor when I increase the noise a bit. So that's kind of interesting because the noise is only 1 to the -2 amplitude, but those excursions are, relatively large compared to the attractor scale. Okay, and then what I might do, I wasn't able to implement this last night, but in a future version of the course, I might try to implement an adaptive Euler integrator where you actually change this dt so the size of the noise step changes at every time. There's a lot of numerical stability issues that you get into when you do that, but you totally could try to implement like an adaptive two-step Euler with stochastic updating. Okay, so that's stochastic integration, and the easiest version is just do it like we did Ornstein-Uhlenbeck, where we just add a random vector, but there's an entire field here that these notes touch on if you're interested in going a little bit deeper into that. Okay, so then the last thing I wanted to talk about with ODEs, because I think that this comes up especially quite a bit for the plasma physics people, is symplectic integration. And this is integration in the presence of a conserved quantity. So all of these update rules that we were doing before, they're just taking the right-hand side of your ODE, pulling it to get a size of the gradient of that space, and then updating along that. But none of those update rules are forced to conserve any sort of quantities like energy, which could be dangerous if I'm doing something like integrating orbiting particles in some magnetic field, or maybe I'm studying n-body simulations in gravity, where I know I have invariants that I have to conserve. So symplectic integrators are all about finding your invariants and making sure that they're conserved. Okay, so I was using this system up here. We're going to say goodbye to that for now because that's not a system with a Hamiltonian. And instead, for these cases, I'm going to use the example of a double pendulum, which is a system that has conserved energy in the absence of friction. So the double pendulum equations are not that interesting, but they look like this if you spend the time typing them out. But importantly, for a double pendulum, I have 4 dynamical variables, which are the angles of the top and bottom pendulum, as well as the angular accelerations or the momenta associated with those 2 pivots. So the double pendulum is a 4-variable chaotic system. If you spend a lot of time writing it out and then solving it, the solution of the double pendulum looks like, let me do this with a good integrator before we use the bad integrator. Okay. That might cook a little bit. We'll see. Hopefully not too long, though. All right, I'll make a note to run this before class next time. Okay, I might have gone too ambitious with my time step here. I'll give that. Okay, I'm just going to integrate it for a lot shorter. Great. I'll run that 4 times as long. Okay, great. Okay, so if I have a double pendulum, if I have a pendulum, the tip of the pendulum moves chaotically. So if I have my double pendulum, the bottom tip moves around. It turns out if you watch a double pendulum, the tip traces out this really erratic attractor. That's provably chaotic. So the tip of the pendulum never does the same thing twice, assuming you have enough initial energy. But importantly, while it's chaotic, the total mechanical energy, so the potential energy plus the kinetic energy of the 2 pendula, should remain conserved. So there is a conserved quantity, even though the system is globally chaotic. Okay, so if I do, so here I used a fancy integrator, I used a built-in, but if I use something less fancy like the Euler integrator, then we start to run into a problem. So we'll see if I regret doing this for such a short time again. Okay, so that's my Euler integrator. Yes. Okay. So my Euler integrator was just a basic fixed step integrator, and it looks like it did okay. Like it still got the fact that it's a chaotic system. But if I keep track of the total mechanical energy, it actually increases over time. And the reason for that, right, is because like the Euler integrator has never heard of a Hamiltonian, right? You just give it the right-hand side, which might be given by Hamilton's equations, but doesn't know about those, and it's just going to update based off of that. And at a finite time step, you can imagine if I am overstepping, so the actual gradient is a little bit smaller than the linearized gradient of the function, then we're going to have this system where it's going to gradually increase the amount of energy in the system because it's going to gradually be adding too much momentum each update because I used a fixed step. And this is a consequence of the fact that on some level, the fixed step integrator is an approximation of the true dynamics, and if that approximation drifts, it can sort of start to diverge from the true behavior of the system. Okay, so mechanical energy increases over time when I use an Euler integrator for my double pendulum, even though the solution actually looks pretty reasonable. If I looked at that, I think that looks like a valid pendulum trajectory. So the question is, can we update the dynamical equations, or can we update our integrator equations to try to preserve the overall mechanical energy? Okay, so the way symplectic integrators work is that if you think of your dynamical update rules as being derived from some conserved quantity, so here let's say I have something like a harmonic system. Implicitly, when we find the right-hand side of the differential equation, we're using Hamilton's equations. And so the way that you can always derive a symplectic update rule is to do an update on one of your 2 variables using something like Euler, plug it into the Hamiltonian, and then solve for the update on the other variable that preserves this quantity. So here I'm going to do it for the harmonic system, but then we'll see how we do it for a double pendulum. So if this is the quantity I want to be conserved, so I want my momentum squared plus my position squared to be conserved. Position squared is conserved because we're using gravitational mechanical energy. I can put in a candidate update where I say that I'm just going to take an Euler step in my momentum, and that Euler step turns out to be this because of Hamilton's equations. But then rather than take the same Euler step for xn plus 1, I'm going to take this Pn and plug it into the Hamiltonian. So I'm going to take what I found, this is what I want to know, and then I'm going to take this and set it equal to the value of my Hamiltonian. And it turns out you can do a whole bunch of algebra on that, and you'll end up deriving that your update rule is that you take a step on your momentum using traditional Euler, but then you take a step on your position using your most recent value of the momentum. And this ends up being the update sequence that preserves the value of this quantity globally. And so all of these symplectic integration schemes always boil down to basically what's called a half step, where I update one dynamical variable, then rather than updating the others, I then take that intermediate value and I update based off of it instead. And it turns out that if you generalize this derivation to the Hamiltonian for the double pendulum, which isn't quite so clean as this, you'll get the same basic idea, which is I have to update one variable, then use that intermediate value to update the other, rather than updating both at once like I do with traditional Euler. And the derivation is a lot less clean as you get more terms in your Hamiltonian. Okay, so if you generalize this and you sort of mess around with it and solve, the general version of this generalized symplectic integrator is update one variable, then take that cache value, use it to compute that, and then update the other. Okay, so symplectic Euler, I've implemented it here, and I'm trying to use the same API where instead of taking the Hamiltonian, it takes Hamilton's equations, which is the right-hand side of your differential equation. And all the logic of this is the same as our fixed step integrator, except for the fact that I do an update on both variables. Then I compute the value of the right-hand side based off the current value of those variables. Then I compute this intermediate update. Then I need to compute the right-hand side again. So I have a second call to my right-hand side using one of those intermediate values. So you can see that x1 instead of x0 appears here. So I use the intermediate value of position that I just updated, and then I'm going to find a new value of the gradient that uses that half update on the position, but p is still the original that came into the loop as. And then I can just update using that second value. And so the half step is the fact that I had to do one update here, use that to do the other update. That's where the half update comes through. Okay, so it's 2 extra calls to my function, but hopefully that's going to get me better energy preservation. And it looks like this takes a while to run, so I won't run it here. So when you run that for a really long time, you get these dynamics. And it turns out that when you look at the mechanical energy, I used a pretty big step here. If you look at the mechanical energy, it does change a little bit, but eventually it plateaus once my integrator converges. And if I get a smaller and smaller time step, eventually mechanical energy will be globally conserved. It just will take longer than 20 seconds to run, so I didn't want to run it in my notebook. So the symplectic integration scheme where I do one update, then I use that intermediate value to recompute the Hamiltonian. In the limit of small time steps, this should always preserve your Hamiltonian. So this is very useful for orbit problems where you have conserved energy. It's very useful in fluid dynamics where you often have a stream function that's conserved. And it comes up a lot in particle dynamics where you have a Hamiltonian. So symplectic integrators are a whole field. This is just a little taste of what they look like. But the whole idea is if you have a known invariant like a Hamiltonian, you could build an integrator around that invariant. All right, I'll go ahead and wrap up there. Thanks.